Okay, so here we have SiN minus, and we want to draw the VSEPR structure for this. So in this case, the VSEPR structure is going to be almost exactly the same as the Lewis dot structure. We're just going to show the angle. So we're going to start by taking silicon, and we're going to triple bond it to nitrogen because we have 10 electrons total. Silicon has 4 valence electrons plus the 5 valence electrons from nitrogen plus 1 electron because of the charge. And so with this many electrons but only 2 atoms, we're going to have to triple bond the silicon to the nitrogen in order to fit all of the electrons on. So let's do that. That's one bond. I'll just draw them in. This is 2 bonds, and then this is 3 bonds. That's our triple bond to our nitrogen. And then we're going to add 1 lone pair on each atom. And so this way, if we count them up, we have 1, 2 electrons from the lone pair on silicon, plus 2, 4, 6 from the bonds, giving us 8, plus the last 2 electrons from the lone pair on nitrogen, and this will give us 10 total electrons. So this is what the Lewis dot structure looks like, and also what the VSEPR structure looks like, with the only addition that we need to make being showing that this angle is, of course, 180 degrees, because it is linear. So now that we've indicated the angle, the only thing left to do for the VSEPR structure is to show that it's an ion, and we do that just by putting brackets around the structure and adding the charge right there in the corner. Lastly, let's just indicate that the molecular geometry is linear, and I'm sorry, I forgot to introduce myself. I'm John Montianu, and I'll be showing you how to draw the contour diagram for SiN minus and also show the hybridization. Okay, so now we're going to draw and show the hybridization of both Si minus and nitrogen, and you're going to have both the silicon and the nitrogen, in this case, hybridizing to form the triple bond in this molecule. And so we're going to show first the silicon and then the nitrogen. So starting with the silicon usually has 4 valence electrons, but because of the charge on it, we're going to include the 5th. So you'll see that as I draw this in. We're going to have 1 electron here, 1 electron here, and that's our 2s orbital filled. And then we're going to have 1 electron here, here, and this is usually where we would stop, but because of the charge, we're going to add that electron in right here. And so now we're going to hybridize directly because we don't need to excite any electrons. And the reason for that is that we want 2 electrons left in the p orbital unhybridized, so that they can participate in the pi bonds that we're going to have once we when we triple bond the silicon to the nitrogen. So we need 2 pi bonds, and that's why we're leaving 2 electrons in the p orbital. And then the rest of these electrons, the 1 in the p orbital and the 2 from the 2s orbital, which I'll circle right now just to make it more clear, these electrons are what we're going to hybridize, and we'll get an sp hybridization orbital because the molecule is linear, and sp is the hybridization for linear molecules. So I'm just going to draw in 1 electron here, 1 electron here, and then the last electron down here. And then for the 2p orbital, we're going to have the same electrons that we had before that did not undergo hybridization, so we have those 2 electrons. And for nitrogen, it's essentially the same thing, because we have the same number of electrons, which I'll draw in right here. We have the same number of electrons, and the only difference is that silicon, in this case, behaved the same way as nitrogen because of the charge on it. So we're going to do the same thing, and we're going to hybridize these 3 electrons, and then leave the 2p, 2 of the 2p electrons alone because they will participate in our pi bonds. So hybridizing those 3, we're going to have this for the sp, and we're going to have this for the 2p orbital, like so. And so now what's going to happen is that we can take the electrons from the 2p orbital of the nitrogen, and this shows that they're being added to the 2p orbitals of the silicon, and this is how our pi bonding is shown. Let me see, like this. This is how we're showing our pi bonding, and then we're going to take the lone electron from the sp orbital and show that it's being added to the sp orbital over here. And that's how we hybridize Si minus and N in this molecule. Okay, so now we're gonna try and draw the contour diagram of the molecule, and please bear with me over here because it might get a little messy, but I'll try my best. So we're going to have silicon over here, and we're going to have our our sp orbital going out like this with our 2 electrons there, and then our nitrogen is going to be over here, and we're going to have also the 2s orbital coming from the nitrogen over here, and this is the sigma bond that nitrogen and silicon share, and this is the first of the 3 triple bonds. And so then we're going to have p orbital here on the silicon, and another p orbital like this on the silicon, and we're going to have the same configuration for the nitrogen, where we have 2 p orbitals like so. And now we have another sp orbital coming out this way with 2 electrons in it, and another sp orbital coming out this way on the silicon with 2 electrons in it. Now these kind of lateral sp orbitals with the 2 electrons in it, these are our lone pairs. These are our lone pairs. And the p orbitals that I've drawn have 1 electron here, 1 electron here, 1 electron here, 1 electron here. And what's happening here is that we're going to have attraction between these 2 p orbitals right here, and this is a pi bond, and then we're going to have attraction between well, I'll draw it on the bottom, I guess. Then we're going to have attraction between these p orbitals over here, and this is our second pi bond. And so now with 2 pi bonds and a sigma bond, let me label this sigma bond, and a sigma bond, that's how we have our triple bond between silicon and nitrogen. And I'll just label this as sp and this as sp, along with these orbitals over here. The angle again for this molecule, like we saw in the VSEPR structure, is going to be 180 degrees and have a linear molecular geometry. And I think that's about it. Actually, we're not quite done yet. I think I just forgot to connect a couple of my p orbitals. I should connect, let me see, these two over here. Yeah, now this is looking more messy, but that orbital and this one over here. Yeah, all of the p orbitals are connected, and that gives us our 2 pi bonds. And now I think we're done.